Hi, so in today's video, we're going to look at the exact sine values, cos values, and tan values of particular values of arguments that we put into those functions. So for particular x values that we substitute into the sin, cos, and tan functions. So there are 5 cases that you need to know off by heart in case you get questions in the exam which ask you for exact values. So sin 0 is 0. That's the first one you need to know. Sine pi over 6, which is basically sine 30 degrees, is a half. Sine pi over 4, so sine 45 degrees, is root 2 over 2, or 1 over root 2. They're the same number. Sin of pi over 3, which is sine 60 degrees, is root 3 over 2. And sine pi over 2 radians, which is sine of 90 degrees, is the number 1. And if you think about like a sin graph, sorry, it doesn't go like that, my bad. A sin graph goes like this, starts at 0. So when x on the x-axis is 0, sin 0 is 0. When you substitute in pi over 2 into that, so sin pi over 2, so sin 90 degrees, you obviously get the number 1 there. So we can see that sin is increasing between x equals 0 up to pi over 2. So it kind of does this pattern here. And something else I'll mention as well is that because of this line of symmetry at x equals pi over 2 between pi and 0 in this part of the domain of the sine function, it means that actually these sin values are reflected across this line of symmetry here. So for example, if sin 0 is 0, that means that sin pi, so sin of pi, is going to be 0 as well, because it's kind of reflected from there over to there. Now, sin of pi over 6 radians, a sin of 30 degrees, roughly about there. So we know that sin of 30 is a half. So we go across from half over to here, then that angle, because of the line of symmetry and the fact that this gap there between that angle, this pi over 6 angle 0, must be the same as the gap between this angle and pi. If we do pi take away pi over 6, that's 5 pi over 6. So that tells us that sin 5 pi over 6 is also equal to a half as well. So that equals a half too. Obviously, we've got again to sine pi over 4, so sine 45 degrees basically is 1 over root 2. Again, we can do the same kind of thing here. So if we do pi take away pi over 4, we would get 3 pi over 4. So actually, because of the line of symmetry again, that means that sine of 3 pi over 4 is equal to the same value as sine of pi over 4. And again, because of the line of symmetry, if sine of pi over 3 is root 3 over 2, sine of pi over 3 is like roughly here. So again, the line of symmetry goes across to there. If we do pi take away pi over 3, we get 2 pi over 3. So that means that sine 2 pi over 3 sine 2 pi over 3 is also equal to root 3 over 2. So again, yeah, that's kind of how you can work out other angles on the other angles that you could substitute into the sine values. So let's think about cos instead. So again, cos 0 is 1. Cos pi over 6, so cos 30 degrees is root 3 over 2. Cos pi over 4, so cos 45 degrees, again, is 1 over root 2, which is the same as root 2 over 2. So the same as sine of pi over 4. Cos of pi over 3 is a half, so cos of 60 degrees, that's a half, and cos of 0 is just 0. So again, this time the cosine graph decreases between x equals 0 and x equals pi, and then increases between x equals pi and x equals 2 pi. So we start from 1 and then go down to, sorry, minus 1 down there. And obviously, yeah, that's pi over 2 there. We can see that cos pi over 2 is 0. Cos 0, obviously, we can see is 1 on the y-axis, and then it decreases like this. So again, if you wanted to work out perhaps some cos values over this side of the x-axis, so using our line of symmetry at x equals pi, we can say with certainty that if we've got pi over 6 roughly there, using the line of symmetry over there, so 2 pi take away pi over 6, so 2 pi is the same as 12 pi over 6. 12 pi over 6 take away pi over 6 is 11 pi over 6. So we know that actually this here is the same as cos of 11 pi over 6 using the line of symmetry. So 11 pi over 6. So that up there would be 11 pi over 6 there. Similar with this one, so cos pi over 4, which is cos 45. So if we do 2 pi, take away pi over 4 using the line of symmetry, so 2 pi take away pi over 4, that would be 8 pi over 2 take away pi over 4, which would be 7 pi over 4. So basically this number there is the same as cos of 7 pi over 4, using again the line of symmetry. And then again with this one here, so cos of 60 degrees, so 360 degrees, 2 pi take away 60 degrees gives you 360 degrees, which in other terms is 5 pi over 6. So let's say you've got pi over 3 there, 2 pi take away pi over 3 is going to give you again 5 pi over 3, I should say. So 5 pi over 3 is over there. So 5 pi over 3, again, that means that cos of 5 pi over 3 is the same as cos of pi over 3, and that's going to be a half. So again, you can use the cos graph to get exact values for angles bigger than 180 degrees or bigger than pi radians. And a similar thing with these tan ones. So the values of tan, so tan 0 is 0. Tan pi over 6 is actually 1 over root 3. That's exactly the same as root 3 over 3. Tan of pi over 4 is 1. Tan of pi over 3 is root 3. And tan of pi over 2 is undefined because we actually have an asymptote when the angle is 90 degrees or pi over 2 radians. So again, if you think about our tan graph, remember the tan graph has a period of 180 degrees. So in other words, it repeats itself every pi radians. So what that tells us is that if we add pi to these angles every time, we get the same values. So basically, yeah, what we can tell then is that this value here, this root 3 over 2, is going to be the same as tan of pi over 6. So tan of pi over 6 plus k pi, where k is an integer. So if k is just a whole number, add k pi to it. Every time you're going to get the same value. So let's say pi over 6 is down there. You get this y value there, root 3 over 3. Add pi to it, you get the next one. Add pi to it, you get the next angle, and so on and so on. So if you just add integers of pi to pi over 6, you get root 3 over 2. Similar idea with this here. So this is going to be tan of pi over 4 plus k pi. So that's always going to be 1. So yeah, so for example, 5 pi over 4, 9 pi over 4, just adding pi every time, that's going to be equal to 1. And again, same thing with this one. If you just keep on adding multiples of pi every time, so a whole number times by pi, because again, we've got this period of pi radians, so the graph repeats itself every pi radians. That means that tan of pi over 3 plus some multiple of pi, some whole number multiple of pi, gives you root 3. So let's look at how we would prove these values then. So we're going to start by proving the angles for pi over 6 and pi over 3. So what you do is you want to draw an equilateral triangle. You can call the sides any length you like, actually, any size you like. I'm just going to call it 2 to make it easy, and you'll see why in a minute. So remember, the angles in a triangle add up to pi radians. So if you've got an equilateral triangle, all angles are equal. All angles must be pi over 3 radians. So we've got, we can draw the split the triangle in half like this. You've got pi over 3 radians there. And then if you split this pi over 3 radians in half again, you'll get pi over 6, because pi over 6 is a half of pi over 3. So then you've got this right angle triangle here. Now, what would the height be of this right angle triangle? So using Pythagoras, if I just call the height h. So using Pythagoras, and the base here is obviously going to be 1, because we chopped our triangle in half. The base of this triangle must be 2, because we have an equilateral triangle. So we've got 1 squared plus h squared equals 2 squared. So 1 plus h squared equals 4. So h squared equals 3. So h equals root 3. So our height is going to be root 3. Let's add that in there. So let's start with pi over 6. So sin of pi over 6. So remember, sine using SOHCAHTOA is opposite over hypotenuse. Opposite to this pi over 6 in this right angle triangle is 1. And the hypotenuse is 2. So sine pi over 6 is 2. Now let's do cos pi over 6 this time. So cos pi over 6. So cos pi over 6 is going to be adjacent to the pi over 6 divided by the hypotenuse. The adjacent is root 2. Root 3, sorry. And the hypotenuse is 2. So we get root 3 over 2 as we wanted. And then tan pi over 6. Remember, that's opposite over adjacent. So opposite is 1. Adjacent to the pi over 6 is root 3. So we get 1 over root 3. Now let's go on to our pi over 3 values. So sin pi over 3. So sin pi over 3, that's going to be, again, opposite the pi over 3 down there. That's the h, which is root 3. So root 3. And divide that by the hypotenuse, which again is 2. So root 3 over 2 for sin 60 degrees. And then if we go to cos 60 degrees, or cos pi over 3 radians. So again, adjacent to the pi over 3 is this number 1. Adjacent divided by hypotenuse, so 1 over 2 for cos pi over 3. And then lastly, our tan, so tan pi over 3, opposite to the pi over 3 divided by the adjacent. So root 3 opposite divided by adjacent, well, divide by 1 because 1 is the adjacent, you just get root 3. So that's how you prove the cases for pi over 6 and pi over 3. And lastly, how about the pi over 4 case? So with this case, you want to draw an isosceles right angle triangle. And again, it doesn't matter what you call these like equal lengths there. You can call them anything. You still get the same result. Let's just call it 1 to make the problem easier. So what would be the hypotenuse of this triangle? So using Pythagoras, it's going to be 1 squared. So like, I'll just call hypotenuse h there. So 1 squared plus 1 squared equals h squared. So 1 squared plus 1 squared is just 2. So 2 equals h squared. So root 2 equals h. So we know that's going to be root 2 there, our hypotenuse. So again, doing, I mean, it doesn't matter which angle we pick, so both pi over 4, but let's pick, I mean, this one down here. So sin of pi over 4 is opposite over hypotenuse. Opposite is 1. Hypotenuse is root 2. So we get 1 over root 2. How about cos of pi over 4? So adjacent to this pi over 4 down there, we have another 1, and the hypotenuse is 2, so 1 over root 2 again, as we expected. And tan pi over 4, so that's going to be opposite over adjacent, 1 divided by 1, well, that's just the number 1. So that's how you can prove these exact values for sin, cos, and tan. And also it's just worth bearing in mind that you can use these exact values to get values of sin pi, which again is 0, sin 5 pi over 6, which is again half, sin 3 pi over 4, which is again 1 over root 2, using the symmetry of the graph, and sin 2 pi over 3. Yeah, that's going to be root 3 over 2 again. So you can use that. And also the cos values using the line of symmetry, x equals pi. You can do yeah, cos of 11 over 6 pi, doing 2 pi take away pi over 6, which gives you 11 over 6 pi. So cos 11 over 6 pi is root 3 over 2. Cos 7 pi over 4 would be root 2 over 2, and cos of 5 pi over 3 would give you a half. So and again, similar with the tan ones as well, because it's got a period of 180 degrees, so pi radians. If you just add pi, multiples of pi, to these 60 degree values, 45 degree values, 60 degree values, you get your exact values for tan. So again, that's just a summary of how you can get the exact values and how you can prove these results.